Imagine walking into your home and the lights automatically know when you need them, turning on only when it's dark and you're actually there, then switching off the moment you leave the room. What if I told you that this isn't science fiction, but a reality we've built using simple, affordable technology? Good morning and Assalamualaikum everyone. My name is Muhammad Yusuf Amir bin Hazri, and today my team Sanjih Kumanaya, Nick Sarah Halina and also Muhammad Hakim will show you how we've created energy efficient smart homes using IoT technology. Our smart lighting technology system doesn't just save energy, it's actively contributing to the SDG 7 affordable and clean energy, one automated decision at a time. And the best part, you can build the system for under 150 ringgit. Let me start by explaining the problem statement that drove our project development in the first place. First major issue that we saw was energy waste in households is a critical problem affecting millions of homes worldwide. We see this daily through lights left on in empty rooms or areas where natural lights would suffice. HVAC systems running at full capacity even when rooms are unoccupied or when temperatures are already comfortable. Second major issue that we faced was this inefficient energy consumption creates a dual impact. Firstly, economic burden. High electricity bills because energy is used unnecessarily. And second, environmental impact. Excessive energy consumption contributes to greenhouse gas emissions like CO2, accelerating climate change and environmental degradation. So, our solution, we've developed a smart lighting system that directly addresses these challenges using ESP32 microcontroller for intelligent processing, LDR sensor for ambient light detection, PIR motion sensor for occupancy detection, Blynk IoT platform for real-time monitoring and control. Now, this system automatically controls lighting based on actual environmental conditions and human presence, ensuring lights are only used when truly needed. Most importantly, our project aligns perfectly with SDG 7 affordable and clean energy by promoting sustainable energy use through automation and real monitoring, ultimately contributing to both cost savings and environmental protection. Now let's dive into how our IoT system architecture makes this intelligent automation possible with our team member Sanjeev Kumanaya. Thank you.
Now, I will be explaining the IoT system architecture of our project. Now, there are four main layers being the perception layer, actuation layer, device connectivity layer, and lastly, the application layer. I'll start with the perception layer. For the perception layer, it is basically where it captures data from the physical environment and then sends it to the ESP32 microcontroller. Components used here would be the LDR and also PI motion sensors. These will be the devices that will be able to capture those data. Eventually, those data will be sent to the ESP32 controller. Now, moving on is the actuation layer. For the actuation layer, this layer will simply act as the layer where actions will be taken based on the data that is given and processed from sensors and also the microcontroller. Now, the components here would be the relay module and also LED. The relay module will inevitably work as a on-off switch for the LED. Now, when it is on or off, that is depending on the data that is captured from the layer above and also what is being processed and sent to the actuation layer. The third layer being the device connectivity layer. Now, for this layer, it basically connects the layer above it to the Wi-Fi. Now, the components used here will be the ESP32 built-in Wi-Fi. Now, this layer aims to be the connect. This layer simply aims to be the connection of local Wi-Fi and also the internet, enabling for remote control and also access to devices. Now, the last layer is the application layer. Now, the components in this layer being Blynk, which is the user interface that will be used to act as a dashboard to show the data and also live updates. In other words, this is where we can see the real-time monitoring of the system.
In this project, complexity arises for both the system architecture and the interactions between its components. The system uses two sensors, an LDR for ambient light and a PIR for motion, working together to determine when the light should turn on. What adds to the complexity to the inclusion of two modes, automatic, which uses sensor input, and manual override via the Blynk app. This means the system must track user preferences while still evaluating sensor data. On top of that, there's a user adjustable lux threshold that changes the behavior of the automatic mode. Real-time communication between the ESP32 and Blynk servers over Wi-Fi also adds network complexity. All of these components must operate seamlessly for the system to work correctly. In our design, every element of complexity introduces a corresponding limitation, and understanding these paired challenges can guide our future improvements. Let's begin with the sensor integration. We combine an LDR for ambient light detection with a PIR sensor for motion. Coordinating these two sensors in real time requires careful calibration and noise filtering. In practice, the LDR can give inconsistent readings under variable lighting due to shadows or reflections, and the PIR only detects motion rather than continuous presence. As for the dual mode operation, our system features both automatic control based on sensor inputs and a manual override via the Blynk app. Switching seamlessly between these modes add complexity to the control logic. This dual mode design has a limitation which can lead to edge cases where the system might misinterpret sensor data against manual commands if not perfectly synchronized. Moving on, for real-time communication, the ESP32 continuously updates the Blynk cloud with the live sensor data and receives control commands over Wi-Fi. This dependency of the over Wi-Fi means that any network latency or connectivity issues can disrupt real-time control with no offline fallback. Lastly, the timing and synchronization. Its complexity is that it contains multiple processes such as sensor data acquisition, relay switching, and UI updates must occur simultaneously and accurately. Its limitation is that even slight delays or asynchronous behavior may cause the system to respond inadequately. For example, if I turn the light on or off at the wrong time. To overcome the current limits and make the system more intelligent, we've identified a few future improvements. One idea is to use camera-based occupancy detection, which can recognize human presence more accurately than a PIR sensor. Another is adding predictive energy optimization. For example, learning when users usually enter a room and preemptively adjusting the lights. We could also expand the system to control fans or AC units, not just lights, using a modular design. On the user side, adding energy usage reports would help households understand and reduce their consumptions. Lastly, implementing offline functionality would allow users to control the system even without internet access, improving reliability. These improvements would take our smart home system closer to a truly intelligent, sustainable solution that supports SDG 7.
In conclusion, we successfully implemented a smart lighting system using ESP32 microcontroller combined with light-dependent resistor LDR and PIR motion sensor. These two sensors will work together to control the light automatically. With this dual sensor setup, the light will turn on when it's too dark and motion is detected, helping to reduce the unnecessary electricity usage in bright or unoccupied spaces. We also added manual override feature on the Blynk IoT dashboard app so that the users can control the light manually, making the system more flexible and user-friendly. Overall, this project supports the SDG 7, affordable and clean energy by promoting energy-saving automation in smart homes.
So this will be our video demonstration for our project for data computer and network DCN. So first of all, I would like to explain the flow chart. So it will give an overview of the flow and how this project actually functions. We'll start off with finding the read motion sensor. Once that has been done, it will bring us to an option of whether motion is detected. If motion is not detected, as you can see on the right here, the light or LED will turn off. Then it will bring us to an exit which will break this loop. However, if motion is detected, it will bring us to the second option here, which is whether we want it to be in manual or not manual mode. If we do not want it to be in manual mode, it will bring us to the third option, which is light condition, whether it's too dark or not too dark. However, if we want it to be in manual mode, there is one more step. We have to read the light sensor. Hence, it will be a manual step. Bring us down to light condition. Now, let's say the light condition is not too dark. This will bring us to this option here, which is an action. The light will turn off and exit the loop. Now let's say the light condition is too dark, which is a yes. Light will turn on and eventually exit the loop. Now we will be presenting about the walkway simulation. I'll pass the presentation to Yusuf Ami.
Okay, thank you, Sanjeev. So today I'll be explaining three critical components of our energy efficient smart homes project: the LDR sensor, the relay module, and also the LED with the corresponding code implementation in our walkway simulation. So number one is the light dependent resistor. So looking at our walkway circuit, you can see the LDR sensor is connected to our ESP32. The LDR is our system's eyes. It's the component that detects how bright or dark the environment is. So the key hardware specification is it is connected to GPIO 34 and analog input pin. The function is just to detect the ambient light intensity. So the working principle is when the resistance changes based on light intensity. Bright light means low resistance, so more current flows, and in dark conditions means high resistance with less current flows. So in our walkway simulation, the LDR forms a voltage divider circuit where the voltage GPIO 34 varies based on the LDR's resistance, which changes with light intensity. So going through the code, we just have um, four functions. Analog read, LDR pin, where it reads the analog voltage from the GPIO 34, which returns a digital value between 0 up to 4095 in the raw output. And the higher values mean brighter light. And the voltage conversion formula is just light level times 3 by 3 3.3 divided by the raw value, which converts digital reading to actual voltage, which we can see 0 or until 3.3 volts. Next, the lux calculation. The formula is just 10 to the power of 2.5 minus voltage divided by 0.8 which converts the voltage to lux units, which is the standard light measurement. So we can see those three outputs in the simulation: raw 1001, voltage 0.81 volts, and lux 31 lux. So the lux value just means for a bright day, which is sunny, it's going to be around 500 lux plus. For evening and at night, it's going to be up to 100 to 500 lux. And if it's really, really dark, meaning there's no light at all, then it's going to be less than 100 lux. So lastly, it will display all the readings on the output for debugging purposes. And next part is the relay module. So the relay module is just our system smart switch. It's the bridge between our low power ESP32 and the higher power LED lighting system. So the connection is via GPIO 12, the digital output pin. The function is just electrically controlled switch. The purpose for the relay module is just to safely control high power devices with low power signals. So the operation, for example, when the motion is detected and the LDR lux value is low, it will just, the ESP32 will send a high signal to control the relay switching. So in our walkway circuit, you can see the ESP32 is connected to the GPIO 12 and to the relay control input, and the relay output is connected to the LED power, meaning the um, positive leg. So the relay is needed just for power isolation, for safety purposes, and for flexibility, meaning we can control AC or DC loads. And the relay control logic is just when it receives high signal, meaning 1, it energizes the relay coil and the contacts close and the LED will turn on. And when it's low signal, meaning 0, it de-energizes the relay coil, contacts will open and the LED will turn off. So lastly is our LED. It's just to represent the controlled lighting device. Is what actually provides the light in our smart home system. So the control method is just via the relay module. The power is supplied by the external power supply, not directly from ESP32. The function is just to give visual representation of our smart lighting system. So that is all from my part. Next, we will go to Hakim, which will explain more detail on the PIR motion sensor.
Hello, I'll be explaining about the PIR motion sensor. First, I'll be explaining about the pins. The PIR sensor is connected to GPIO 4 with a virtual pin named vpin_motion and is labeled as V7 to connect to the Blynk application. Moving on to the main function of the PIR sensor, which is named detect motion. The main function of the PIR sensor uses in the detect. It reads the PIR sensor state when it is high when motion detected and low when no motion is detected. It only updates Blynk and serial when motion state changes and sends updates to virtual pin vpin_motion v7 in Blynk app. And within the light control function, the code that shows the condition for both light level and motion detection for light to turn on is light should be on equal lux value less than threshold and motion detected. This shows that the lux value needs to be below the threshold set and also motion detection for the light to be on. When we simulate the motion within walkway, we could see within the terminal simulate motion. We could see within the terminal motion detector and the light turns on. It follows the condition that we set where it needs motion to be detected and light to be less than threshold value. That's all from me. Now I'll pass to Sanjeev to explain the outputs.
Okay, for the output, I'll be explaining two essential parts of what has the output produced. The first part being here. So as we can see here, what is trying to be displayed is connecting to walkway gas, connecting to Wi-Fi, and this given IP address. What this means is the ESP32 is trying to connect to the simulated Wi-Fi network, which here is walkway gas. And it's successfully connected and got the IP. In this case, the IP is 10.10.0.2. Now, the other important part that I would like to show is here. Now, what the output simply states is connecting to blynk.cloud, redirecting to sgp1.blynk.cloud, and ready ping 213 milliseconds. Now, what this is basically, it is the ESP32 trying to connect to the Blynk cloud server. Then it is redirected to a Singapore server here, sgp1.blynk.cloud. And then they're connected with a ping type of 213 ms. And as stated below there, Blynk is successfully connected. That is all for my part from the output. Now I'll be passing the presentation to Sarah to explain the Blynk section.
Now I will show how our smart lighting system works using the Blynk IoT platform. We're using two sensors in the system, an LDR to measure the brightness of the environment and a motion sensor to detect any movement. So as you can see on the Blynk dashboard, there's various of gadgets, starting with the light status switch, shows whether the LED is currently on or off. It's an automatic indicator based on the sensor readings and control logic. There's also threshold control slider. So it lets users to set the lux threshold. If the LDR value falls below this threshold and motion is detected, the LED will turn on automatically. So in our case, we set it to 500 lux. Light level gauge displays the current light intensity in lux unit from the LDR. Next is the light condition label. It shows a descriptive message based on the current lux level to help users easily understand the surrounding brightness. So when the lux value is above 100, it shows too bright. If it's below 100, it displays too dark. And if it's between 50 to 100, it shows normal light. Then we have manual mode toggle switch. So it will act as the master switch. Next is the manual light control switch. It only works when manual mode is on. It allows user to manually turn the LED on or off regardless of sensor inputs. And lastly is the motion sensor gauge. It shows whether the motion is detected, 1 for motion present and 0 for no motion. So now I will demonstrate how this system works. So as you can see, the lux value is below 50, it's 31. So if the lux value is below 50, it indicates too dark. And when the motion sensor detect motions, which is 1, the LED will turn on. When the lux value is above 100, for example, here 199, the light condition indicates too bright. Even when the sensor detect any motion, the LED will not turn on because it's too bright already. If the last value is between 50 to 100, for example, like 74, so the light condition now is in normal light. So normal light, when there's motion, it will turn on the LED. So for our system, we also implemented manual mode activation where users can fully control the light regardless of the sensor readings. So when the manual mode toggle is switched on, it acts as the master switch, activating the manual control. So if the manual light control is also turned on, the LED will turn on even if the environment is already bright. So even the light is too bright, the LED still turn on because we activate this manual mode. If the manual light control is turned off, the LED will remain off even if it's too dark. And even there's like motion, the LED will remain off. So this allows users to override the automatic light system whenever needed. So in conclusion, our smart lighting system offers both automatic control using the LDR and motion sensors, as well as manual override through Blynk, giving users flexibility, energy efficiency, and real-time monitoring, all from a mobile dashboard. That's all from me.
Hello everyone, I'll be demonstrating the Wireshark demonstration for this DCN project. Over here I have my physical ESP32 cam, which I'm just using without any input or output, just to show that the Wi-Fi module for our code is working and can be seen within Wireshark. Over here we can see the IP address of the ESP32 connected to the hotspot of my laptop is 192.168.137.227. The ESP32 is using the exact same code that we use within our simulation. The only difference is that I only want to show the Wi-Fi right now and not the actual input and output. Over here you can see the same thing that we showed within our demonstration for our simulation. The same outputs, the same code, except I changed the Wi-Fi module to my hotspot. My laptop's IP address is 192.168.137.1. It is connected to local area connection 2. And if I run my Wireshark right now, and if I ping this IP over here, send 4, receives 4. Stop right there, and we can see if I filter it by ICMP, which is if you ping. The source 192.168.137. Okay, you can see that the pinging and echoing request and reply is working. This means my ESP32 is successfully connected to the internet using the Wi-Fi. Thank you very much.